Thank you. So in this last lecture, I will finish the construction of the Floer complex. So remember that yesterday we finished with showing that this space of Floer solutions of finite energy was compact in this topology. So this was what I call Gromov compactness. Now today I will start with the compactness of the compactness which is actually needed for the construction of the Floer complex, which is the compactness of the trajectory spaces. But before that, I have to give a consequence of Gromov compactness, which is needed to prove this. I didn't prove yet that any Floer trajectory joins two critical points. I only show that at the limit we have critical values, right? So this is useful. As in Moore theory, you know that every gradient trajectory joins two critical points of the Morse function, which I didn't yet prove. So the consequence would be then that M is the union for X and Y critical points of these spaces M, X, Y I spoke about in yesterday. So which means that every trajectory joins two critical points. Now let me prove this. So to prove this, consider for each critical point, so fix some R, and I will do this argument in omega, which is this domain of A, which are the build of chords paths from L to L, right? So let me define a distance here, say d between X and Z is the supremum for K less than R of and T between 0 and 1 of the norm of X K T minus Z K T. So this enables me to define balls. So let epsilon greater than 0 and define this ball for X critical. Define this ball X epsilon is the Z such that the distance is less than epsilon. And suppose that these balls are mutually disjoint for X in the. So we have this in omega. We have these balls of epsilon radius, and then take U in M. Okay. So if we denote the U capital, the union of these balls, what I want to prove is actually that I want to prove that for some S greater than epsilon, S epsilon, US is in this union U. This suffices to prove that at plus infinity I will I will tend to towards a critical point, right? Now, if not, there is some Sn going to plus infinity such that U Sn is not in U. And so I will consider the sequence U S plus Sn. So this is a sequence in N. So since M is compact, it will, by compactness, U S plus Sn will go to some V which lives in M. Okay? Now, V, let's show that this V is actually it is actually a constant trajectory. To prove this, it's not very difficult, because if you write this, which is the limit of this expression, now remember that I show that this is a critical value of A. Okay, so this is A of Z critical value. But what is important here that it doesn't depend on S. So actually, the function on this trajectory is constant, which means that the trajectory V is actually a critical point. And this is contradictory, because this means that U S n goes to V. Okay, and V must be among the center of the balls I drawn here, which is impossible because USN was supposed to be outside U, right? So this ends the proof. Question? Now, let me go to this compactness of trajectory spaces. So what is the compactness we need? If I draw a picture in a Morse theory picture with the deformed two-sphere with the height function, now what you can see that the space of trajectories from here to here is not compact. It will one sequence of trajectory here can converge to a broken trajectory on the sphere. So let me formalize this thing in our framework. So let's define for x and y critical points the space of broken trajectories Lxy bar, which is one I talked about in the very beginning. I needed to have some compact one manifold with boundary, which I called L bar. So this is L bar xy, which is the union of Lx z1 times Lx z2 z1 z2 times L zk minus 1 y, say, where zi are critical. Okay. So these are broken trajectories from x to y, right? And on this space I will put a topology. Actually, I will only say, for our purposes sufficient, when a sequence un of unbroken trajectories converges un converges to some broken trajectory. So this is, by definition, if there is some, is for some real sequences S1n, S2n, Skn, we have, yeah, actually I will denote this by U hat, and UN will be a representative in MXY. Okay, so we have so then again we have UN of S plus Sn I T goes to UI, and then M, which means in C infinity log. So it means when taking a representative here and translating with some sequence, we have this convergence in the space of solutions in M, in C infinite log. Okay. And let me emphasize here that this is consistent with the. This is consistent with the quotient topology. On L. I mean, when we have an unbroken sequence of unbroken trajectories, the convergence I defined here is exactly the one one should define on L as coming from M, right? And so the compactness I need is the following. So theorem of proposition L bar xy is compact. And now again, I will only prove that for what we need, we only need that to show that a sequence of unbroken trajectories admits a subsequence which converges to a broken trajectory. Okay. So the proof. Let UN be a sequence in L, X, Y. And what I will do is I will, as before, take these balls. X. So Z epsilon for any Z critical point of H. And again, I will do my proof in this space of trajectories in omega. So these are these balls. And so we have from here, from X to Y, we have this sequence of trajectories UN. Right. Now, let's consider here UN SN1. So SN1 is the first exit point from Bx epsilon. So the first x time from this ball, which means that UNS is in this ball for S less than SN1, and UN SN1 is on the boundary. And then, just take as a sequence in M this one, Un S plus Sn1, and this converges to something which I called U1 in this whole space of solutions by Gromov compactness, right? Okay. Now, what can be said about this U1? So we know that if S is less than 0, then U1 of S is the limit of this, and the limit of this is a limit of a sequence which is in Bx epsilon. So U1 of S belongs at least to B bar x epsilon. Okay. And then again, for S equal to 0, U1 of 0 is a limit of elements which are on the boundary, so it belongs to the boundary. Okay. So this means that this U1 is a trajectory which starts from X, and it's not constant because it reaches the boundary, right? So U1 is something which belongs to M starting from X, non-constant, so it goes to another critical point, Z1. So let me picture this here. So this is Un of Sn1, and this is this trajectory U1 going to Z1. Now, if Z1 is X with Y, we are finished. If not, we proceed as follows. We know that, so for S bigger to some S star, this trajectory is in the ball. Right, because its limit is Z1. And then, so from this time S star is in the ball. So this means that for the time Sn1 plus S star, Un is also in this ball. So this means that Un Sn1 plus S star belongs to this ball for n large enough. So then consider, on the other hand, this trajectory has to exit the ball because it has to travel until y. So at some point it should leave the ball. So let Sn2 be the first exit point. Sn2 greater than this one be the first exit point. After Sn1 plus S star. So we have, therefore, that Un of S is in this ball if S belongs to Sn1 plus S star and Sn2. And in Sn2, it exits the ball, so it belongs to this boundary. Okay. Now, of course, we want to take Sn2 as the second sequence needed in the convergence, but before we have to prove some lemma. Which says that Sn2 minus Sn1 goes to plus infinity. Okay. Now, the proof is not difficult, so prove. If not, so Sn2 minus Sn1 goes to some finite limit. And then we consider this Un of Sn2, right? And we write it like Un of Sn1 plus Sn2 minus Sn1. And then we use the first convergence, because the first convergence was C infinite lock, and this one goes to sigma star, so it's in a fixed interval. So we know that this goes to U1 of sigma star. Right? But U1 of sigma star was contained, U1 of sigma star was contained in the interior of the ball. Whereas this one is on the boundary of the ball. So this is contradictory. So therefore we have this lemma, which is quite, I mean, this is not surprising because, of course, between the sequences we have in the definition, yeah, all the sequences in this definition have differences which go to infinity because they lead to different trajectories in the limit, of course. Okay. Now, what we take then, of course, is Un S plus Sn2, and this goes to a U2 in M. Okay. And so again, as before, for S less than 0, then S plus Sn2 is less than Sn2 and greater than, and now we need to be in the ball, so you put this here, Sn1 plus S star. And this is true because of this lemma, right? So for S greater than 0, we are exactly in the interval where UN was in the ball, okay? Which means that U to S is in this closed ball, right? And now now U2 of Sn2, U2 of Un of Un of Sn2 is in the boundary. So therefore, U2 of 0 is in the boundary, which means again that these two conditions imply that U2 belongs to, so starts from Z1 and goes to another critical point Z2. And then we proceed in an analogous manner to find other broken orbits. Of course, at some point this process has to end, because each time we find another critical point, because the functional decreases, for instance, and actually the index too. So this finishes the proof of the compactness. Well, so this means that by now we prove the following thing. So we prove that if say the difference of indices is 1, then Lx, y is a zero-dimensional manifold which is compact. It's compact because in this case we cannot have broken trajectories in the limit, because we cannot have the difference of indices. There are no difference of indices available to have these broken trajectories, right? So this enables one to define this nxy. So dx is the sum of. This enables one to define the differential, right? Because the number is finite. So then, if the difference of indices is 2, we show that Lxy is a one-dimensional manifold. And we show that this L bar xy, which is Lxy union with Lxz times Lzy, is compact. In this case, a sequence can only break once, of course, because again of the difference of indexes. At each break, we have to lower strictly the index, right? Yeah. Because at some point, at every for instance, at every step, the index is lower. No, probably not. It's not the right thing. No, not the fact that the index is lower. The fact that the action decreases strictly. Yeah, but you find another critical point. There are no finite number of them. Yeah, there are no only finite. So the action is lower, and they are only finite. So now what we need to have in order to have our complex defined is that, so the last part is the part which is called gluing, meaning that this is a one-dimensional manifold with boundary. And actually what we have to do is the boundary structure at this point, these points, right? And so what we need is when we take u and v in L, x, z, L, z, y. So here we are in, here I recall that the difference of indices is 2. So we need to have, we want a parametrization psi rho of unbroken trajectories. Psi of rho goes, when rho goes to plus infinity, to uv with this topology. So this is the last step. There were 3 main steps. There were transversality, compactness, and boundary structure, or gluing here. So this is the last step of the construction. Now, it's called gluing because of the method. Now let u, v be representatives in mx, z, and mz, zy. And what we do is the first thing we do is some operation we call pre-gluing. So I will only say the main idea of this gluing procedure. It's a very technical one. Now, the idea is the following. First, we have to build a pre-gluing, which means that, let me define them as cylinders. So this is x, this is y, this is z, and then you go with the u until a big time rho minus 1, and then here you start from v with the very negative time 1 minus rho, and between the both you do some interpolation. So you do some things like this in order to have a smooth trajectory. So a formula will be f w rho st is u s plus rho t for s smaller than -1, v s minus rho t for s greater than 1, and here's something to interpolate and to have it smooth. Now, of course, this is not a solution of the Floer equation. So we only have that this is 0 if s is greater than 1 because of in absolute value, because of this formula. So one should think of that as some approximate solution of the Floer equation from which you want to build a genuine solution. And let me emphasize also that if you can say here that, of course, this has no meaning with respect to the space I defined, because W rho is not a real solution, but a genuine solution. But this goes to UV. This goes to UV with the convergence I defined, because when you take this as minus rho t, this is exactly UST for s greater, smaller than rho minus 1. And s plus rho t is VST for s bigger than 1 minus rho. So in the C infinity log topology, we have convergence. So this W rho has the good properties, except for the most important one, which is it's not a solution. So we have to build, starting from this W rho, a genuine solution. And what we do is something which, I don't know if this is the good name for it, but we called it in our book Newton Picard method. Well, the Newton method is something like this. You, for the real function, say. So you want to find a root of the real function. So you start from some point here, x0, and then you approximate. So this is x0 is the approximate solution, and then you take the tangent here, and you find the point, your point x1. So this is x0. You take the tangent here. So you find the point x1. And then normally in the Newton method, you take the tangent there. But what we do, and what one does here, take the same, a line with the same slope here, parallel line. And then you find x1, x2, and so on, and then you approach this solution. Okay? Now, what would be this function here? The role of this function f is played by the following one. So this, I mean, I think the interpolation here is something like this. Xn is xn minus 1 minus f xn minus 1 divided by f prime xn minus 1. Things like this. So this is somehow the basic formula you have in mind when you proceed to this approximation in the gluing framework. X0. This is, yeah, of course. Because, this is the original Newton method, but we use this one, right? Yeah. So the role of this function f is f rho, which is defined by on this W1P of. So these are Sobolev vector fields along this approximate solution, and we send them into LP with the formula f rho of y is exponential the Floer operator applied to the exponential like this. Okay. Which means that the initial point here, x0, corresponds to y equal to 0, and it corresponds so to W rho, which is the pre-gluing. Okay. Now, we have to consider, therefore, this differential, L rho, this differential, L rho, which is the d0 of f rho. Now, this differential going to W1p to LP, it's not, of course, it's not bijective. Actually, one can prove, remember that the difference of indexes here is 2, and this L rho at the asymptotics has the same asymptotics as the usual Floer operator. So what we can prove here is that L rho is Fredholm of index 2. So this is kind of immediate consequence of the Fredholm property we had in the transversality. But moreover, actually what we prove is that L rho is surjective and admits right inverse, moreover. J rho from LP to W1P. So this is the crucial point here in the gluing operation. And how do we actually use this J rho? So this J rho plays the role of 1 over f prime here, okay? And if one denotes by W rho the image of this inverse J rho, G rho, what we do actually, if I draw a picture in C infinity xy, so this is C infinity xy, and here we have this W rho, and close to it we have this space of dimension 2. Okay. Now this is of codimension 2. Since this is Fredholm of index 2, so surjective, so it's kind of a supplementary of this of its kernel. So it's of codimension 2. And what we do here is to intersect this space of solution with exponential W rho of this supplementary space. Okay, so geometrically the picture is this one. We just intersect this two-dimensional space with this codimensional space. At the intersection we get of this solution, this genuine solution psi rho. Okay. Now, of course, technically speaking, it goes along this line. So we have to write this this relation. So this relation here has to be something like xn is, I hope I'm not mistaken, G rho L rho x n minus 1 minus f rho J rho f rho x n minus 1. So this relation is this one in our setting. So when at the limit we find when we apply L rho here, because of this property of right index, we find that f rho of the limit, so xn goes to some, then f rho of the limit is 0. Okay, so then of course, what one has to do is to put all the say technical condition in order to have this Newton method to function, which means it's a fixed point method. So you have to ensure that at some point this sequence is a Cauchy sequence that it's convergent. Okay. So yeah.
So don't we have to worry perhaps about the fact that the blue slopes can get too vertical? So perhaps need the right inverse to be bounded or something.
You need the
blue lines there.
Yeah.
That it gets too vertical.
Yeah. I mean, of course, you have to worry about all these things. I mean, you have at some point you have to put the right condition in order to have this recurrence to go into a convergent sequence. So there are some technical fixed point conditions which you have to prove by hand. Yeah. Yeah. Of course. Wait. Yeah.
I think what, if I understand correctly, Humberto wants to say that you should add, and it's easy to add in the second proposition, the fact that you prove that the inverse G rho is uniformly bounded in rho.
Yeah. Of course. Yeah. But I mean, this is of course this is true. But what I do here is it's a fixed rho. Okay.
Yes. But
I mean the interpolation is this interpolation is done at rho fixed.
Absolutely. But the writing that uniform boundedness is absolutely crucial if you want to show that the solution that you get in the end satisfies the same geometric condition of converging to the rho that you get.
Yeah. I mean, there are many conditions to be made. Of course, to be put there. Of course, I show this one. We want that this y here to be small enough in order to still have this convergence we had with the initial point. So there are many technical things to be done there. So this is just a very rough idea. Yeah.
So another thing that we can point out at this level is that subjectivity goes for rho large enough.
Yeah. Probably I should say. Yeah. Right. Okay. Now, yeah. So, with all this in. With all this done, then we finished the construction of our Floer complex, and so we can define. So therefore, we define and therefore this Floer homology. And afterwards, we have to show that it's invariant. So let me say just a few words about invariant. So Alex talked about this yesterday. So invariance means that if we choose two couples of Hamiltonian, regular Hamiltonian, and almost complex structure, then the Floer homology associated to these two couples are the same. Now, this is what is what Alex called continuation, and it's done by choosing a path between the two, which is HA, GA for S very small, and HB, GB, JB for S very large, and define, take as a trajectory space the space of solutions of this equation, this parameterized equation, plus gradient HS equal to 0. So actually what we look at is some solutions of this equation of finite energy. Solutions which start as solutions for HA, GA, and then this is the parameterized part, and then they end as solution for HB, GB. And actually, it's I mean, here some. One should be a little bit careful in the non-compact setting, because there are some difference between the compact and non-compact setting. We need at some point to have the uniform bound on energy. So the uniform bound here is the maximum, as before, is the maximum of differences of critical values. So X, Y critical. But one should add here supremum of dH, ds. X, X in W and S in R. So therefore, when W is not compact, what you have to do is first to take with a cutoff function, take HA with compact support outside the compact where all the Floer trajectory lie in, right? And the same for HB. And then you join them with the path with compact support in order to have this uniform bound on the energy ensured, right? And so with this one, we get that MAB is a compact, and we have MAB is the union of MXY. So it joins critical points for HA with a critical point of HB, and we have the fact that, let's consider this case. So if mu x minus mu y is equal to 0, then MAB xy is finite, so compact, zero dimension. Forgot to say that MAB is of dimension, manifold of dimension, mu x minus mu y. And if the difference is 1, then this space is compact. X LAXZ times MAB ZY union M X MAB X Z prime times L B Z prime Y. So what I mean here is that this kind of trajectories break as broken trajectories, starting with some broken trajectories for HA, JA, followed by one parameterized trajectory, and then followed by some broken trajectory of the for the HB JB. So we have this thing which is compact. I forgot to union L union M A B X Y. So this turns out to be a one-dimensional manifold with boundary. And this enables one to define this continuation morphism between the complex phi of x is the sum of mxy y, and this property tells you exactly that this is the morphism of complexes. And then what you do is that you go from AGA to HB JB, and then back to HAJA. So you get here a morphism of complexes, here another morphism of complexes. And then from this one, you can go with the morphism given by the identity, the constant path between the two. And this morphism for the constant path between the two is exactly the identity. For a simple reason, because in this case, mxy, if the indexes are the same, in an unparameterized case, if the indices are the same, you cannot have, because of the R action, you cannot have trajectories between x and y, except for the case when x is equal to y. And then your trajectory is the constant trajectory. So mxy here is x if x is equal to y and no trajectory. And then, of course, you have a lot of work to do in order to prove that these two morphisms induce the same morphism in homology. So this is the last part of this invariance property. Okay. And so, in the end, let me tell you something about relation between Morse and Floer homology. So now, so again, Alex said something about it yesterday. Let me just give some hints about the Lagrangian setup. So the proposition is if pi 2 v w. So these were my technical condition. I will weaken them a little bit later, then the Floer homology of W is with some index shift, which is this one, I think, and the Floer homology, the relative Floer homology, is I think the shift is correct. The shift is correct. Yeah. Yes. So now let me say something in the relative case. So in the relative case, of course you can, since you proved invariance, you can choose the Hamiltonian isotopy at your convenience. Of course, it has to be regular, which is not an easy problem. But if you forget about the regularity aspect, just let L Lagrangian, and then you have this Weinstein neighborhood. Right? And you choose as Hamiltonian in this. So as Hamiltonian isotopy, let's put like this. So let F a Morse function. And as Hamiltonian isotopy, you put the one given by the graph, with the translation with the graph of F. So I will take it small enough in order to remain inside the Weinstein neighborhood, right? And for this one, actually, you never go back from the zero section to itself, except for the case you do not move off the zero section. So actually here, the only critical point of this functional are the critical points of F. And therefore the Floer trajectories here are just some disks like this. Instead of half cylinders, the extremities of half cylinders are just these critical points of F, right? And among them, so these are Floer trajectories. So among them you have, of course, as Alex told us, among them we have those which are independent of time. And those one are just the gradient lines. And so the result is that if F is small enough, and J is well chosen, then for mu x minus mu y equal to 1 each, trajectory is independent of time. Okay. So therefore, the Floer homology coincides to the Morse homology. Actually, there are two aspects here. The one is the local aspect, in which you take this Lagrangian, and it's in this Weinstein neighborhood, where everything is like in the cotangent space. And so the first thing you have to prove is that in this, taking here well-chosen almost complex structure, you only have the trajectories which are inside are independent of time. So this is one, so the local aspect is concerned with the trajectories in UL. And then one has to show that in this, with this hypothesis, there is, if f is sufficiently small, there is no Floer trajectory going outside this Weinstein neighborhood. So if f is small enough, no trajectory goes outside U. And this is a consequence of, this is actually a consequence of Gromov compactness. Because if you have, for f, say if for f equal to 1n, fn equal to 1 once you're 1 on nf, you have un whose image is not in U, then by Gromov compactness, this converges to some U star in C infinite log. But this U star is actually a holomorphic disk with boundary on L and non-constant. Holomorphic because this term turns to 0, okay? And we have this kind of picture, and we use the removal singularity theorem to find the holomorphic disk. But this kind of disk cannot exist in this with this hypothesis, because its symplectic area is 0, and this disk is non-constant. So just have in mind that these are two different aspects: the local one and the global one, which in this setting does not play a role because there are no holomorphic trajectories going outside this Weinstein neighborhood. Okay. Now, of course, this implies, this proposition, or implies as a corollary, the Arnold conjecture. So this is an easy consequence because you have the Morse inequality saying that the number of critical points of AH is greater than the dimension of the Floer homology, and this one is the dimension of the usual homology. So in the relative case, or in the absolute case, this is the proof of the Arnold conjecture with the Floer setting. And this one, in the relative case, remember that it was the number of, so in my, so with this correspondence gamma, I don't know if you remember that, this corresponded to the intersection points between the Lagrangian and this Hamiltonian deformation. So what you proved here is that this number of points, which is the same, which is the same actually, of course, phi1 of L, is bounded below by the homology of the Lagrangian manifold. Okay. Now, in the remaining 20 minutes, let me tell you something about some more general settings. Because this condition is, of course, very restrictive, so one of the weaker condition one can put in is this one. Now, what we have here is that, so this is well defined, no bubbling. Remember that to ban holomorphic spheres and disks, the only condition which was used is this one, meaning that the symplectic area of one disk of one sphere was on one side 0 and on the other side, because of the fact that the disk was holomorphic, it was non-zero. So this was the contradiction I used in compactness. But the only difference here is that the Maslov index is not well defined in Z. Actually, you have defined it in a Z on an L. So in particular, MXY may have components of various dimensions. Okay. But of course, so the dimension, the local dimension at one, let me adopt here the point of view which with two Lagrangians. So the local dimension is given by what is called Maslov Viterbo index, which is built by considering the loop with taking tangent Lagrangians on one side and here transverse Lagrangian planes in order to have a loop for which we define a Maslov index. Of course, with respect to the Arnold conjecture, this is not very this is not very different, because in any case I didn't use here any, I didn't make any reference to degrees. So yeah.
In this case, do you have a grading in Floer homology?
No, I do not have an absolute grading in Floer homology. Relative grading. It's a relative grading. So this is only defined with respect. Of course, if you change this strip between x and y, you may have a different dimension. This is what. Okay. So this was the first one. The second one is more different than the other one. Is the case of monotone Lagrangians. For which I remember this meant that the Maslov morphism is positively proportional with the integration morphism on pi to WL. Now, what happens here is that if you have a holomorphic sphere or disk, holomorphic disk, W its Maslov index, its symplectic area is positive, of course, and its Maslov index must be so greater than 0. Right? On the other hand, one can show that if you if you take a space of solutions of dimension, a component of dimension k, and you take here a sequence, right? If you take a sequence here. So this of course, this problem, all those problems are related to the failure of compactness, okay? So if you take a sequence here, and with some bubbling W in the limit, then the Maslov number of this W cannot exceed there is some additivity of Maslov numbers, which implies that the Maslov number of this bubbling disk which occurs cannot exceed the dimension of the, which is still a Maslov number, the dimension of the space we are consider. Okay. On the other hand, this means here that if it's greater than 0, then it's greater is greater than the Maslov number of the Lagrangian manifold. So what you can put here as a condition in order to have this Floer homology is defined, because you only use spaces of dimension less than 2 in the construction, we just simply put if NL is greater or equal to 3, then Floer homology is well defined. Okay. Now let me just say a few words here about the relation with Morse homology. In this monotone case. So remember, there were two aspects. The local aspect, in which we can arrange ourselves to have only trajectories which are, let me consider this situation. So L and then F, a small Morse function. So in this case, our complex CFL, even if the Floer complex is not graded, here we have a grading given by the Morse index, because the critical points are the critical points of F. So we have this grading given by the Morse index. So the Floer complex is the Morse complex of F, or K in N. And now we have this, we have locally on one side, we have this, if you choose for a well-chosen almost complex structure, we have locally only these Morse trajectories from X to Y. But globally, you can have, in this case, there's no more contradiction as here. So you might have Floer trajectories which go outside UL. Okay. So this, I cannot explain it very exactly, but these Floer trajectories have a positive symplectic area, and one can show that fact if U is a Floer trajectory in M, X, Y of dimension equal to 1 going outside U, then the difference of Morse indices must be minus 1 minus chi k and L, things like this. Okay. So in this case, one can write the Floer differential as being a sum where this is the Morse differential, and then dk goes from ck to ck minus 1, from ci minus 1 plus k and l. Okay, so this is the sum. This is the sum which is made along this number k. So in this case, the differential decomposes as the sum. And now, when one writes this relation by using the different gradings, what you find is that the first one is the Morse relation, of course, and then you find this one. And this just means that delta 1 can be defined on the usual homology of L, right? Of course, with this shifting grading. The third one just tells you that d1 square here is 0. So this enables you to define a homology of the homology. Okay? And then the other one, the next one, tells that d2 can be defined on this homology of the homology. And so on. So you get this, say, A infinity homology of L with all these procedure. And actually, what is hidden here is a spectral sequence. So O spectral sequence. So I will just state is as follows: H infinity of L is 0. The Floer homology of L is 0. Okay, so in this case, there is no isomorphism a priori between Floer and Morse, but we have a spectral sequence starting from a page which is built with Morse homology and ending up with an H infinite with a limit which spans a Floer homology, right? And I will finish with the simple proof of Audin's conjecture coming from these considerations. Now, the Audin conjecture was the following: if L is in R to N monotone Lagrangian aspherical, which means that pi I of L is 0 for I greater than 0, then 2, sorry. Then the number, the Maslov number is 2 or 1, depending if orientable or not. Now, it works like this. So I will take the point of view with two Lagrangians, right? So when we take two Lagrangians, so you have to look at holomorphic strips joining critical points of the function, right? Now what you do is you forget about everything which doesn't lie on L. So for this kind of holomorphic strip, UST, you only consider this path US0, which is a path in L. Okay? And then with this path, you just lift those paths to the universal cover. And you define a complex with the universal on the universal cover, which is defined as follows. Actually, you can take any cover you like. So this is P. So the complex on the universal cover is defined is spanned by all the fibers of the intersection point. So it's a infinite dimensional complex. And as a differential, dx bar is the sum of n x bar, y bar, and nx bar, y bar is the number of u in L, x, y, so it's finite, of course, such that u s0 lifts between x bar and y bar. So therefore you have a complex. You have a complex. Why? Because what you do here, in order to have a complex, we have this broken trajectories properties, right? So actually, as in Morse theory, in what I did, broken trajectories come by pairs. Okay, so if you see the broken trajectories here, a pair of broken trajectories which are whose extremities are joined by a continuous one parameter family of unbroken trajectories, this just draws you on L this kind of picture. You see this kind of pictures on L, just taking what you see on L, taking t equal to 0. So you see these pictures there. It's kind of Morse picture. And then when you lift this Morse picture, because it's contractible, you lift these broken trajectories and they will come by pairs upstairs, right? So this very easy argument enables you to say that what you defined here is a complex. And now you still have, so if you want to relate its homology to the Morse homology, you do the same things. So you do this all this procedure with a small function, and you have all these differentials. So you have this spectral sequence, and this spectral sequence starts with what the lifting of the Morse complex computes upstairs. And the lifting of the Morse complex upstairs computes exactly the homology of the universal cover. Okay? So actually what you see here is that you have this D1 from age. So I mean what you have to suppose here is that of course NL is greater than 3. So for NL greater than 3, you have this D1 going from the HI of the universal cover to HI of -1 plus NL of this very universal cover. Okay? And when you take, so actually all these groups are 0 except for H0. So you have D1, H0, L, and this one goes to 0. So this H0 does not die in under the action of the homology defined by delta 1. And for the same reason, it doesn't die for delta 2, for delta 3, and for delta everything. This means that it survives in the limit of the spectral sequence. So this means that H infinity of L cannot be 0 because it contains this element. But on the other hand, we live in R to N, so L, when you take an appropriate translation, this can be displaced. So the Floer homology must be 0. Now this is a contradiction. And this proves the Audin conjecture for a monotone aspherical manifold. I think I will stop.